to it in a second here. All right, here we go. So, calculus was invented by Newton and Leibniz came up with this integration notation that we have here. And it says, whatever the function is, we'll go from -4 up to x of the function. Okay? This is basically f of x dx, where dx is the first derivative of f of x. And if we integrate, then we'll get to that later this week. So I'll get to why everything is the way it is later in the week. But what we do in the fundamental theorem of calculus, we take this and plug it in here. And if it's more than just x, then we take the derivative of it as well, the dt. Okay? So this is just f of x from -4 to whatever it says. Okay? Now, they want to evaluate it at -2, then it's basically from -4 to -2. Okay? Because it says evaluate this at -2. So what we're doing is evaluating how much area is under the curve from -4 to -2. Well, it's really easy to figure out this much area because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 squares there. So the area is 12. Here, it's 1 wide by 2 tall, and it's a triangle. So it's 1/2 the base times the height. So 1/2 of 1 times 2 is 1. And here, another triangle, 1/2 the base times the height is 1/2. So this is then, if this is 12, this is 13.5. So the fundamental theorem of calculus allows you to find the area under the curve from certain points using an integral. And we'll get more into integral notation and how integrals work later this week. Okay, but that would be 13.5. So for this one, it wants us to evaluate g of 4. So it says h of x, we want to find from 1 to 4. Okay, what is the area then under the curve from 1 to 4? Well, I split this into two separate trapezoids now. Okay, because it makes perfect trapezoids. This one is 3 and 4, so you take 1/2 of 2 times 3 plus 4 plus 1/2 of 1, because this is 1 wide, this is 2 wide, this is 1 wide, this is 3, of 1 times 4 plus 3. Well, 1/2 of 2 is 1, so this is 7. The area under here is 7. Okay, the area under here is 1/2 times 1 times 7 is 7/2, or 3.5. So you get 10.5. That's the area under the curve. That's what an integral finds, is the area under a curve. So if we're told to find this, we stick the x in for the there, and stick the x in there. Well, the first derivative of x is 1. So it's just the square root of 2x plus 7, where x is this number. 2 times 9 is 18, plus 7 is 25. So we're taking the square root of 25, which is 5. Fundamental theorem of calculus done. You don't even worry about the first number. Okay? Don't worry about the first number. You just worry about this one, the one the x is. Okay? So the sine of t, which is the sine of x, which is then the sine of pi. Okay? What is the sine of pi? Well, at pi, on the unit circle, we're right there, which is 0. Okay? For this one, because we have more complicated than just x, it's a square root of x, we're going to put it there and there. So it is the derivative of this, which you take the square root of x and you square it, because it's t squared, times the first derivative of the square root of x, which is x times 1/2 over square root of x. X over square root of x is square root of x on top, so it's square root of x over 2. For this one, x squared, following the same premise as what we did last time, the x squared goes here and the x squared goes there. So it's x squared squared over x squared squared plus 1 times the first derivative of x squared. So it's x to the fourth over x to the fourth plus 1 times 2x, because the first derivative of x squared is 2x. So it's 2x to the fifth over x to the fourth plus 1. We're done. Fundamental theorem of calculus. Take the top number, plug it in, take the derivative of it. So, excuse me, this one. Square root of 1 plus what? 2x cubed times the derivative of 2x. So it's 2, because that's the derivative of it, times the square root of 1 plus 8x cubed. Okay, and that's all it is. Okay, now this is a graph of f. What's appropriate calculus-based justification that this is concave up? Now, we got to think backwards here, okay? This is the regular function, okay? This is the regular function here. Now, if we're integrating it, this is like the derivative. And what would the regular function look like? Well, if you have a positive slope that's above the x-axis, what's the regular function look like? And it's increasing, right? It's increasing because it's above the x-axis. And it's increasing faster. So what's appropriate that it's concave up? Because this is increasing. Why do we have an inflection point there? Well, the inflection point happens when the first derivative is at a maximum. Okay, so if the first derivative is at a maximum, that's where the inflection point is at. So that's the types of things you'll get assigned to today. So we have 66 minutes in here. I've used 10 of it. You've got 56 minutes left to work on the last assignments you've been working on and getting these done. All right, there you go.